What we need to now look ahead to in the course is to try to expand the category of varieties. Okay. So far we have been looking at affine varieties and quasi affine varieties, which are open subsets of affine varieties, but then we need to also include more general varieties, and the next in this list are the projective varieties and the quasi projective varieties. And the projective varieties are they have properties which are very different from the properties of affine varieties. Okay. So you know what I wanted to start with is since we are looking at we have been looking at affine varieties. Okay. The first thing I wanted to say is about the so called Jacobian conjecture, which is a very simply stated conjecture, but which is open even in the simplest case. Okay. And the reason it makes sense to talk about that conjecture now is because you know what automorphisms, you know what morphisms of varieties are, you know what are isomorphisms of varieties, and you know how to characterize isomorphisms of affine varieties. Okay. So I'll first recall the following thing from the previous lecture. So if you recall, X any variety, of course here for us any variety will mean either affine variety or quasi affine variety. Okay. And Y an affine variety, which means Y is an irreducible closed subset of some affine space over an algebraically closed field, of course. Then we have a natural bijection So on the one hand you have morphism of varieties from X to Y that is bijective to homomorphisms of K algebras from AY to OX. Okay, we proved this bijection, and in fact what was the if you recall this map, if I call this map as alpha, then how is this map defined? It's the map in this direction is just given by pullback of regular functions. Okay, so you know, in other words, if f from X to Y is an element on this side, namely it's a morphism from the variety X to the affine variety Y, then you send it to alpha f this alpha f is going to be a K algebra homomorphism from the ring of polynomial functions on y to the regular functions on x, and that is very easy. Namely, you give me a polynomial function, let me put it as p on let me put it as yeah, capital P, give me a polynomial function capital P on y, okay, you compose it with f to get a regular function on x. Note that a of y is the affine coordinate ring of y, the coordinate ring of functions, polynomial functions on y. It is just polynomials restricted to y, and these are the polynomial functions on the affine space in which y sits. Y is an affine variety, so y sits inside some an, the ambient, the bigger affine space, and on this bigger ambient affine space you have the polynomials in n variables, and each of these polynomial functions by evaluation defines a map into k, which can be thought of as a map into a1, and it is a regular function of course, and you restrict such polynomials to any subset, in particular to y, and you get a polynomial function on y. The only thing is that this polynomial function on y is not represented by a unique polynomial, it is represented up to addition by a polynomial in the ideal of y, okay, which consists of polynomials which vanish on y, okay. So give me a polynomial restricted to y and I just compose it with f, first apply p then apply f, that's a regular function on x, because a polynomial function restricted to y is of course a regular function on y, and what is happening is I have a regular function on y, and then by composing it with f I get the pullback of the regular function on x, and the pullback of a regular function has to be a regular function because f is a morphism, because that is already built into the definition of a morphism. So this is how this map is defined, okay, and there is also if you look at the map in the reverse direction, alpha inverse, how is that defined? Well, give me a homomorphism phi from K algebra homomorphism from ay to ox, okay, and then of course you know if of course you know you assume that y is thought of as sitting inside affine space and ay is just, well, k of is identified with k of x1 xn, which is the polynomials on the affine space, the xi being the coordinate functions divided by the ideal of y, okay, and so what you do is that you just take the xi, you take the xi bars which are elements here, they are the images of xi in this quotient, okay. So xi bar just denotes the coset xi plus iy in the quotient ring, okay, and you simply send it to a certain function, let us call it as hi, it is a regular function on x, and the fact is that you will what will happen is that from x to an you will have a map which will send any point x small x to this h1x, this n tuple defined by the h's hn of x, because I have n of the xi's, so I have their images here which are n of the xi bars, so I get n of the hi's, okay, and then I evaluate this point at each of these n functions, I get an n tuple which is a point in an, this is the map, and the fact is that this map will factor through a morphism G through the closed irreducible closed subvariety y of an, this diagram will commute and this phi will be nothing but alpha of G, this is the surjectivity, okay. So start with the phi here, then you get these hi's, using the hi's you define a morphism of x into an, the morphism will land inside y, and if you call that morphism as G, then alpha of G is the phi that you started with, okay. That is the surjectivity that gives all the surjectivity, and that also defines how that the alpha inverse of phi is this G, okay. G is just alpha inverse of phi. This is how you get the inverse map, and that is how this is a bijection, okay. And as a corollary to this, what happens is that if you know if X is also an affine variety, then OX can be replaced by AX, because for an affine variety the ring of regular functions, it can be naturally identified with the polynomials restricted to the affine variety, okay. So and alpha will take a bijection to a bijection, okay, and therefore what it will tell you is that if X is also affine, then X and Y are alpha, in fact I should say alpha will take an isomorphism to an isomorphism, okay, that is an invertible, not just a bijection but an invertible morphism to an invertible morphism. An invertible morphism varieties will go to an invertible ring homomorphism, okay, that is a ring isomorphism. An isomorphism of varieties will go to an isomorphism of K algebras, in fact, okay. So alpha will carry isomorphisms to isomorphisms provided you know X is affine, alright, and what that will tell you is that it will tell you that two affine varieties are isomorphic if and only if they are coordinate rings, affine coordinate rings, that is just the rings of polynomials on those varieties are isomorphic. So the corollary to this is X affine and Y affine are isomorphic if and only if AX and AY are isomorphic. Of course this the isomorphism, when I say X and Y are affine and isomorphic, there I mean isomorphism as varieties, and when I say AX and AY are isomorphic, I mean isomorphism as K algebras, okay. So two affine varieties are isomorphic if and only if they are rings of polynomials, the rings of polynomial functions on those affine varieties are isomorphic as K algebras, okay. And how many such isomorphisms are there? There are as many isomorphisms here as there are isomorphisms here, okay. So you know as a particular case what you can do is, well you know I can take for X and Y just an itself. So you know take X equal to Y is equal to an. So what you will get is you will get morphisms of varieties from an to an is bijective to the K algebra homomorphisms from A of an to A of an to A of an, and of course you know A of an is just the polynomial ring. So you know if you want well both of these are equal to K if you want x1 etc xn, okay, if you take them to be the ring of polynomials, if you take the ring of polynomials to be the ring of polynomials in n indeterminates xi's, okay. And in particular if I look at the automorphisms, so the word automorphism means a self isomorphism. It's a morphism is from one object to another object. An automorphism is a morphism from the object back into itself, and in fact a morphism of an object back into itself in general is called an endomorphism, okay, and an invertible endomorphism is called an automorphism, okay. So here of course when I say morphisms from an to an, actually I am looking at the endomorphisms of an. So this is all the endomorphisms, these are maps from an back into itself, they are endomorphisms. So of course the you know the other notation is endomorphisms as varieties of an, and of course here what I will have is endomorphisms as k algebras of the polynomial ring A of an. Okay, and what are the automorphisms? The automorphisms are the invertible endomorphisms. They are endomorphisms which are also isomorphisms. Okay, so they are self maps, they are morphisms of the object back into itself which can be inverted. Okay, so if you look at the automorphisms, that's of course a this, if you look at it carefully, this is a group, because the composition of two morphisms is again a morphism, therefore the composition of two automorphisms is again an automorphism. So this is a group, and on the other hand you also have a group here, this is automorphisms as k algebras of k well let me write as A of an. Okay, so and then alpha carries automorphisms to automorphisms. Okay, so this alpha will also give you a map like this. Okay, you start with a morphism is an isomorphism, which means it is here if and only if its image is here, and conversely. Okay, and now the you see the Jacobian conjecture is connected with automorphisms of the polynomial ring. Alright, so let me make a statement. So what I want to look at is let's take any morphism from an to an. Okay, how is it going to be given? It's going to be given by n polynomials in the n variables. Okay, any element phi of or let me use f of morphisms of varieties from an to an is given by polynomials in fact so let me write this f1 etc fn in n variables. So n polynomials in n variables, that's right, that's just because of this bijection. Okay, so you know what are all these, you know I start with, so here is my f from an to an, then you know I have this is mapped, that's this point, that's an element here, it's mapped to an element here which is alpha of f, and this alpha of f is a map from, well, k x1 etc xn to k x1 etc xn, where I am identifying the ring of polynomials on an with k x1 etc xn. Okay, and how is from a polynomial ring a map is dictated by the images of the variables. So you know if I take alpha f of xi, this is what alpha f takes xi to, and this n tuple dictates the k algebra homomorphism alpha of f because of the universal property of the polynomial. Okay, so what I want to tell you is that and it's these alpha f of xi's that I am calling as fi's. Okay, so let me write that here. I need a better duster. So I have xi going to alpha of f of xi, okay, and I am calling this as fi. Okay, so essentially what you are doing is that corresponding to this morphism an to an, that corresponds to giving me n polynomials, okay, and that is what I have written in the previous line, that a morphism from a n to n is simply given by n polynomials in n variables, okay. And when is this morphism an isomorphism? When it has an inverse, okay. F is an automorphism, that is it is a invertible morphism, namely an isomorphism, if it has an inverse, okay, and so it has an inverse F inverse. So you see what will happen is I will have an F inverse which again will go from an to an, okay, and that will be mapped under alpha to alpha of F inverse. That will turn out to be again a map K algebra homomorphism from the polynomial ring in n variables to again to itself, back into itself, and that is again going to be dictated by the images of the xi's under this, so alpha of F inverse of xi, okay. And well, if I call this as, you know, if I call this as gi, which means I am just calling F inverse as g, okay, by my previous notation. If f goes to f1 etc fn, then F inverse equal to g will go to g1 etc gn, alright. And what you can see immediately is that see you will have, if I start with a point x1 etc, if I start with a point with coordinates lambda 1 etc lambda n, that will go under, if I apply the map f to it, what I am going to get is f1 of lambda 1 lambda n and so on fn of lambda 1 etc lambda n. This is the point it is going to go to, okay. That is what it means to send the xi's to fi's under alpha of f, okay. And now this point is, if I apply F inverse which is g, this point has to go back to this, but under F inverse where will this point go? See, this point will go to g1 of f1 of the lambdas. I will put it like this, dot 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 gn of f1 lambda fn lambda. This is what it means. So what, where of course, you know, where lambda underline is just lambda 1 through lambda n, okay. So what you get is g I of f1 lambda etc fn lambda is simply lambda I for every I. This is what happens if you have an automorphism, right. And now what you can do is, you know, this holds for all lambdas, okay. So you can write this in variable form as gi of f1 of x fn of x is equal to xi for every I. You can write this in variable form, okay, which makes sense, alright. And then, you know, for example, if you want, you can take the partial derivative on both sides with respect to any xj. You will get, of course, if it is x, if you take partial derivative with respect to xi, you will get 1 on the right side. If you take partial derivative with respect to xj of j not equal to I, you will get 0. Then what you can check is that you can check that the Jacobian of dou Fi by dou Xj is a non-zero constant. In K. Okay. So what you must understand is that, you see, I take each of these polynomials, each of these Fi's, each Fi is a polynomial in n variables, and if I differentiate partially with respect to each variable, I will again get a bunch of polynomials. Okay, I have n polynomials, I have the n Fi's, I differentiate each n of them with respect to the n variables, so I will get I get this Jacobian matrix. Okay, that is in general going to be a matrix of polynomials again, because you take a polynomial in n variables and differentiate it partially with respect to one of the variables, the resulting is the resulting thing is again a polynomial in n variables. Okay, and then therefore if you look at the Jacobian determinant, then in fact I think the correct maybe it is better to write it as, of course here x underline stands for x1 through xn, and maybe it is better to write this as Jacobian of f and call it like this. Okay, and the point I want to make is that, you see, if you calculate this Jacobian determinant, it is going to only be, you expect it only to be a polynomial, because every entry is a polynomial gotten by taking a partial derivative with respect to certain one of the variables. But the fact is f has an inverse g, okay, and therefore, you know, if you write down everything, f followed by f inverse is identity. Okay, and for the identity function, if you take the Jacobian, you will simply get the identity matrix. Okay, so finally what will happen is that you will see that the Jacobian polynomial of f into Jacobian polynomial of g will, if you take the product polynomial, it will be equal to 1, which will be the Jacobian polynomial of the identity map, which is just the identity matrix. So you have product of two polynomials equal to 1, so each of them has to be a constant, it has to be a non-zero constant, that is why Jacobian of f will be a non-zero constant. So what this simple argument shows so far is that, you know, if I start with an automorphism, okay, I end up with you know a bunch of functions, I end up with n polynomial functions. If I start with an automorphism f, I end up with n polynomial functions whose Jacobian is a non-zero constant. Okay, that the converse of this is true is the Jacobian conjecture. Okay, so the Jacobian conjecture is if f is not known to be, f is not given to be an isomorphism, initially, does then the condition that the Jacobian of f is a non-zero constant implies f is an automorphism. Okay, this is the Jacobian conjecture. The Jacobian conjecture is that if I start with an f which I do not know is invertible, I do not know it is an isomorphism, but suppose I have the condition that if you take the Jacobian of f, namely you take the Jacobian of these n polynomials that specifies f, okay, under this correspondence, if this Jacobian is in generally you expect it only to be a polynomial in n variables, but suppose it turns out to be a non-constant, I mean a non-zero constant polynomial, then the Jacobian conjecture says that f should be invertible. That means you should be able to find another set of polynomials, n polynomials, which if you plug in to f, the f's you will get back identity, okay. That is the Jacobian conjecture, and the point is that somehow another way of stating that is that you know, there is a map from here to the polynomial ring given by taking determinant of the Jacobian, okay. Every endomorphism is given by n polynomials and you take the Jacobian determinant of those n polynomials, you will get a polynomial. So you get a map from this endomorphism to your ring of polynomials, and what we have seen is that the inverse image of k star, that is non-zero elements of k, that well, that contains this, okay. Namely, every automorphism for every automorphism the Jacobian is a non-zero constant, but the question is whether if you take the inverse image, okay, then it will be exactly this, that is the question, okay. Namely, if you give me n polynomials, okay, for which the Jacobian determinant is non-zero constant, do those n polynomials actually correspond to an automorphism is the question. So the question is whether the inverse image of the non-zero constants under the Jacobian determinant map from this endomorphism is exactly this. We know it contains this, but what is required to show is that this is exactly this, okay. That is the Jacobian conjecture, and the beautiful thing is that even for k equal to complex numbers and even for n equal to 2, just polynomials in 2 variables, this is open, okay, and it is a very difficult problem. And the beautiful thing is that in the case of complex numbers we have also complex analysis, holomorphic functions, we have that theory also, but it does not seem to have helped, okay. So this is a very deep problem, and being able to solve this or being able to give a counter example to this is worth being awarded by a Fields Medal, which is the equivalent of the Nobel Prize in mathematics. So that is the depth of the problem. It is a very hard problem called the Jacobian conjecture, and the point is it can be stated now because you people know that there is a bijection between, you know, morphisms of affine varieties and k algebra homomorphisms of their coordinate rings. So that is the reason why I want to state it here. So maybe I hope that many or at least some of you will go ahead and try to tackle this problem in your future career, okay. Alright, so now this is just to bring in this Jacobian conjecture. What I want to do now is I want to go to the question of more general varieties, okay. So this is what I want to do next, right. Now so let me give first an example. So what are the varieties that we know so far? We know affine varieties and we know quasi-affine varieties, okay, and quasi-affine varieties are open subsets of affine varieties, and you know that there are quasi-affine varieties which are actually affine, and for example basic open subsets, they are all quasi-affine varieties, but they are actually isomorphic to affine varieties in an affine space of one higher dimension, okay, because of the so called Rabinovich trick, okay. So the basic open set defined by non-vanishing of a polynomial is a quasi-affine variety in that affine space, but in an affine space of dimension 1 more it becomes a closed irreducible closed subvariety, okay. Now the question you can ask is, are there quasi-affine varieties which are not affine? So I want to give an example of such a specimen, okay, and just to tell you that there are quasi-affine varieties which are not affine varieties. So here is a fact, so here is a claim, or I can just put it as lemma. A2k minus the origin is not affine. is quasi affine but not affine. So here is the lemma. Actually it is more than a lemma, it is you can call it a theorem, because you are going to use this result, and you know that this result is it's a grand version of the Nullstellensatz. So it is very bad to call it a lemma, but anyway I will call it a lemma, alright. So and it's usually or maybe I will have second thoughts and at least call it proposition. So so what are we going to do? See, first let us understand the statement. It is quasi affine because it is an open subset of an affine variety, namely it is an open subset of A2 and it is a non-empty open subset, okay, because I have only deleted the origin, alright, it is a complement to the origin. So it is a non-empty open subset, so it is certainly a quasi affine variety, but I want to show it is not affine. What do you mean by saying it is not affine? What I mean by that is it cannot be isomorphic to any affine variety. That means you cannot find an isomorphism of this punctured plane, okay, this is the punctured plane. This punctured plane you cannot find an isomorphism of that with an irreducible closed subset of any affine space, that is what it means, okay, that is what it means to say that it is not affine, right. So it means that if I take any map from the punctured plane into any affine space, certainly it's never ever going to be a closed embedding, I can never expect it to be a closed embedding, alright. So you see it is like if you state it in this generality, it looks, the proof looks very difficult to verify, because you are trying to say that I will have to just try to think of look at all possible maps, morphisms of this into various affine spaces, and I will have to check that each one of these is not a embedding onto a closed subset, it is not an isomorphism onto a closed subset, that is what it means, okay. But the way we prove it is rather we use all the techniques that we have developed so far, at least some of them. So we prove by contradiction, we go by contradiction. So suppose A2 minus a point, A2 minus the origin, punctured plane is affine, okay. Now again what that means is that I am assuming that it is isomorphic to an affine variety, okay. So see, if it is affine, then it has an affine coordinate ring, alright. So then we have a bijection. As we have seen, there is this bijection alpha, which is morphisms of varieties from A2 minus a point minus the origin to A2. So I have this map from this into homomorphisms of K algebras from A of A2 to O of A2 minus a point, okay. So I have this bijection that I have already written down here, okay. The set of morphisms from any variety into an affine variety is in bijection with the set of all K algebra homomorphisms from the coordinate ring of the target affine variety to the regular functions on the source variety, right. So I am just applying that here, but I am noting that well, since I have assumed A2 minus a point to be an affine variety, this can be replaced by A of that, okay. And of course so this can be replaced by A of A2 minus 0 comma 0, and what this means is that, what does this mean? This means, see, because I have assumed A2 minus a point is affine, there is some embedding of it as some embedding of it into some affine space, some big affine space, I do not know what dimension, and certainly dimension greater than or equal to 2, alright. and in that affine space, since it is realized as a closed subvariety, I take the ring of polynomial functions there, and that is what this A means, and these two are one and the same. Okay, that is something that we have proved for an affine variety. The regular functions and the ring of polynomials are one and the same. Okay, of course by polynomials I mean polynomials restricted to the affine variety, right. So now so in particular, you know, I will look at the canonical inclusion. I look at the inclusion map A2 k minus the origin. This is sitting inside A2, and there is a natural inclusion map. There is this map, so let me put the I here. Okay, then I will get, this will go to alpha of I. Okay, and what is this alpha of I? This alpha of I is going to be a map from k of, let me write this like this, k of x1 etc xn to you know O of well, A2 k minus the origin. Okay, I will have this. Now the you know that under this bijective correspondence, okay, oh sorry, I should not write x1 etc xn, it should be only just x1 x2, sorry, of course. Yeah, thank you. Yeah, so alpha I is from k x1 x2 because it's just affine space, two dimensional affine space, it's just polynomials in two variables, so that n I wrote below before was equal to 2, right. So I have this map, see, okay, so what I had told you is that under this bijection, you see I told you isomorphisms correspond to isomorphisms. Okay, what I will prove, what you can actually see is that alpha of I is actually an isomorphism, therefore it will mean that I has to be an isomorphism, but I cannot be an isomorphism because it is not even surjective, because there is a point missing. Okay, so that is how you will get the contradiction. Okay, then this contradiction will prove that A2 minus a point cannot be identified with any closed subvariety of any affine space, so it is not affine. Okay, so we claim that alpha of I is an isomorphism. This would imply that I is an isomorphism, and that is a contradiction. So this contradiction will prove that our assumption, our original supposition that the punctured plane is affine is wrong. Okay, so this proof proceeds by contradiction, right. So how to show that alpha of I is an isomorphism? Okay, there are two things that need to be done. It is a k-algebra homomorphism, I have to show it is injective, then I have to show it is surjective. Okay, so let me explain why alpha of I is injective. So first of all, let us understand what alpha of I is. Alpha of I is a you know, this alpha is just the map that is induced by pullback of regular functions. Okay, so what is the meaning of alpha of I? It means you give me an element here, namely it is a polynomial in two variables, so it is a function on this A2. Okay, and if you compose it with I, which amounts to just restricting the polynomial to the punctured plane, that is what it goes to. So it is just a polynomial going to polynomial restricted to A2 minus a point, A2 minus the origin. This is what the map is, because pull back means you take a regular function on the target, you compose it with the map. In this case the morphism is I, but composing a morphism with I is the same as restricting that morphism, because I is just the inclusion of this subset. Okay, so pulling back a map under an inclusion is just restriction to the subset corresponding to the inclusion. So what is this alpha of I? It is just take a polynomial and restrict it to the punctured plane. Okay, now how would I show that alpha of I is a injective homomorphism? By showing its kernel is 0, because after all it is a k-algebra homomorphism. To check it is injective I have to just show its kernel is 0. So if I have a polynomial function, okay, if I have a polynomial which if I restrict to a2 minus a point vanishes, okay, then it vanishes everywhere, because you see if a polynomial vanishes on a set, it will also vanish on the closure of the set because of the continuity of a polynomial for the Zariski topology, okay. Therefore if the polynomial vanishes, if this is 0, then you are saying that the polynomial restricted to the punctured plane is 0, but the punctured plane is a dense open, it is an open subset, it is a dense open subset. Any non-empty open subset is irreducible and dense, okay. Therefore this polynomial is going to vanish on a dense open subset, therefore it will vanish everywhere by continuity. So what it will tell you is that this polynomial as a function vanishes everywhere, and in this case because we are working with an infinite field, the field is an algebraically closed field, so it is infinite. So if a polynomial vanishes as a function, then it has to vanish as a polynomial. So see, so that tells you that alpha of I is injective, okay. So alpha of I of P is equal to P restricted to a2 minus the origin is equal to 0 implies P equal to 0. So alpha of I is injective. This tells you that alpha of I is injective. The only thing that I will have to now prove is that alpha of I is surjective. If I prove that, then I am done, then I would have proved that alpha of I is an isomorphism, and we would get the contradiction that we want, alright. So how do I prove it is surjective? So we do it like this. So well alpha of I is surjective. How do I prove this? Well, so what I do is I start with the regular function on the punctured plane, and I have to show that it is given by the restriction of a polynomial, okay. So what is the statement? I start with the regular function on the punctured plane, and I have to prove that this regular function is nothing but restriction of a polynomial in two variables, okay. So start with a regular function phi on the punctured plane to show phi is equal to restriction of a polynomial in k x1 x2. This is what I have to prove, right. This is what I have to prove. Now so you know so let me draw a diagram. So you have something like this, you have the origin, this is a2, and I have thrown out the origin, so I will put a circle here, okay. So this is the punctured plane, and I have a regular function on this, namely well I have a phi which takes values in a1, right. So this is my phi, and I have to show this phi is actually coming from a polynomial, right. And what is the meaning of saying that this is a regular function? Let us go back into that. Give me any point x in a2, okay, then you know I can find an affine neighborhood. I can find a neighborhood of x ux, okay. So you know so this is a neighborhood of x, okay, and this is I must admit that this diagram is not accurate because the neighborhood does not look like that. Any neighborhood of a point is going to be a non-empty open set, so it will be dense, okay. So more ideally I should think of the neighborhood well as a complement of some curves, okay, right. This is how it should look like, but then you know so you know if I take a neighborhood ux of the point x, it is the complement of bunch of curves, alright, because the only closed subset the closed subsets here are curves, and these are the one dimensional closed subsets, and the 0 dimensional closed subsets will be points. So it will be the complement of some curves and some maybe finitely many points, okay. That is how an open set here will look like. So given a point x, I have this neighborhood ux, and then what I have is the fact that it is a regular function means that on this ux it is given by a quotient of polynomials with the denominator polynomial not vanishing on ux, okay. So let me write that there exists an open set, open of course the Zariski topology, ux containing x and polynomials g I gx hx in kx x1 x2 such that phi restricted to ux is the same as gx by hx restricted to ux, and hx does not vanish on ux, okay. This is the definition of what a regular function is. A regular function is something that is locally given by quotients of polynomials, and to make sense of the function defined by a quotient of polynomials, the denominator polynomial should not vanish because you can't divide by 0, okay. So this is what it means, alright. But now notice that the what I need to prove is that phi comes from a polynomial, alright, and if phi came from a polynomial, then that polynomial restricted to ux will be equal to this quotient of polynomials restricted to ux, okay. And you know if I cross multiply it, what I will get is that I will get hx times that polynomial equal to gx everywhere, okay, because the fact is if two polynomial functions agree on an open set, they agree everywhere. If two regular functions agree on an open set, they agree everywhere, okay. The reason is because open sets are dense, and polynomial functions, regular functions, they are all continuous, and if a continuous function is 0 on a non-empty open set, it is identically 0. So if two continuous functions are equal on a non-empty on a dense set, okay, then they have to be equal everywhere. If two continuous functions are equal on a dense set, then they have to be equal everywhere by continuity, alright. So what this will tell you is that, you know, finally I have to prove phi is a polynomial, okay. So it will tell you that hx has to divide gx, okay. It will tell you that the polynomial will be equal to gx by hx on ux, okay. But if I cross multiply, it will tell you that polynomial into hx is equal to gx on ux, but then that will mean polynomial into hx equal to gx on whole affine space, because if two polynomials coincide on a non-empty open set, they are the same, okay. So what it will finally tell you is that hx divides gx, okay. So to obtain a contradiction, I will assume hx does not divide gx, and I will try to obtain a contradiction. So assume hx does not divide gx for every x. I assume that, of course, you know, I am in the polynomial ring, which is a unique factorization domain, and it makes sense to talk about when one divides the other, because you have unique factorization. Any polynomial can be uniquely factored into irreducible polynomials. So so this assumption is this assumption will be true only if phi does not come from a polynomial function, mind you, please understand. I have to prove phi comes from a polynomial function, okay. In other words, I have to show phi is just restriction of a polynomial, alright. But if phi is a restriction of a polynomial, it will mean that h divides g, okay. Conversely, if H divides G, alright, then phi will be the restriction of a polynomial, alright. So if you assume phi does not come from a polynomial, which means if you assume surjectivity is false, then you are actually assuming that Hx does not divide Gx, that is what you are assuming, okay. So let us assume that and come to a contradiction. Now note that on Ux intersection Ux prime we have, well, Gx by Hx is equal to Gx prime by Hx prime, okay, you will have this, alright, and that will tell you that Gx Hx prime is equal to Gx prime Hx, alright, and now you see Hx divides the right side, so Hx divides this, but Hx does not divide Gx, so it has to divide Hx prime, okay, and you will similarly get Hx prime divides Hx. So the moral of the story is that Hx and Hx prime will differ by a non-zero constant, okay. So this will tell you that Hx prime is equal to some lambda x x prime into Hx, this is what you will get, okay. That is because you see Hx, let me again repeat the argument, Hx divides the left side, so Hx divides this product, so it has to divide, but it does not divide Gx, that is our assumption, so it has to divide Hx prime, but this argument is symmetric in x and x prime, so you will also get Hx prime divides Hx, okay, and therefore if two polynomials divide each other they have to just be constant multiples of one another, and that constant of course should be a non-zero constant, okay. So this lambda x x prime is not 0, and well if you put that back into this, what you will get is that you will get that Gx into lambda x x prime is equal to Gx prime, you will get this, okay. So it also tells you that the G's are they differ by a non-zero constant multiple of one another, alright. Now what I am going to do is I am going to do the following thing, A2 k is Noetherian, this is Noetherian, and any subspace of a topological space that is Noetherian is also Noetherian, so this will tell you that A2 minus the punctured plane, A2 minus 0 0, A2 minus the origin is also Noetherian, and Noetherian topological space is quasi compact, okay. Therefore what will happen is that so what you will get is that this is quasi compact, so you will get A2 minus is quasi compact. In fact one characterization of Noetherian topological space is that every a topological space is Noetherian if and only if every subset is quasi compact, okay. So this is quasi compact, but if I take all the Ux's as x varies in A2 minus a point, I get an open cover for A2 minus a point, and that is quasi compact, so finitely many of these should be enough to cover A2 minus a point. So this implies that the open cover Ux x belonging to A2 minus a point, A2 the punctured plane has a finite subcover say Ux1 union Uxn Uxm is equal to A2 minus a point, okay. And mind you each open set is being taken in A2 minus a point, okay, alright. I am for every point in this I am looking at an open set there, alright. If you want the only problem is that this open subset might contain the origin, but then you can throw it out, you can simply throw it out from that open set and replace it with, you can puncture it at the origin if it contains the origin. So you see this, therefore this union will be this, alright. Now well you see what this will tell you is that if you look at it, it will tell you that all the see the Hx does not vanish on Ux, okay. So it will tell you that Ux is contained in dHx okay. So it will tell you that Ux is contained in dHx, alright, and therefore what it will tell you is that all the dHx, the corresponding dHx's will certainly contain this, alright. So this will tell you that dHx1 union dHxn xm will be A2 minus this point, or it may even be A2 itself, okay. So in any case every dHx contains Ux, so you know if you take the union of all these dHx's, it has to contain this punctured plane, it might even contain the origin, alright. Now what I want to tell you is that each of these has a meaning. If you exhaust each case you will get the contradiction. If dHx1 union dHxn is equal to A2, if that is equal to the punctured plane, what this will tell you is if you take complements it will tell you z of Hx1 Hxn is the point, okay, because you know if I take complement of dH I will get zh, and intersection of all the zh is just z of this, okay. But you see for a point this is actually z of the maximal ideal x1 x2, because the point 0, 0 corresponds to the 0 set of the maximal ideal x1, x2, alright. So but you see and mind you that you know all the h's they are all multiples of constant multiples of one another. So if you look at the 0 set of all the h's, it is essentially the 0 set of a single polynomial, and you are saying the 0 set of a single polynomial is a point, which cannot happen because the 0 set of a single polynomial has to be a curve, okay, because you know that there are these we have seen this in one of the earlier lectures, that there is a notion of geometric hypersurface and there is a notion of commutative algebraic hypersurface. It is a locus which is given by vanishing of single polynomial and it has a dimension 1 less, okay. So if all the h's are just multiples of one polynomial, then this is just the 0 set of one polynomial, and you are saying a 0 set of one polynomial in two variables is just a point, that cannot happen. The 0 set of a polynomial in two variables has to be a union of hypersurfaces. So in this case it should be a union of curves, it cannot be a single point. So that is a contradiction, okay. The 0 set of a single polynomial in two variables cannot be a single point. On the other hand, so the other possibility is that the union of all this is A2, okay. If the union of all these things is A2, it will tell you that all the this is something that we have already seen. It means that all the h's will generate the unit ideal. The ideal generated by the h's will be the whole polynomial, okay. If d hx1 dhxm is A2, what it will mean is that z of hx1 hxm is a null set, okay, and this means that the ideal generated by hx1 hxm is the whole polynomial, because one version of the notion says that if you take a proper ideal, a non-trivial ideal, then the 0 set of the ideal cannot be the null set, okay. So the 0 set of an ideal is a null set if and only if that ideal is a unit ideal, right. So but then but all the H's are all multiples of one another, so you are saying that this polynomial ring in two variables is generated by a single element, and that is again a contradiction, okay. So again a contradiction, okay. It is a contradiction because all the Hxi's are multiples of one another, so this is the ideal generated by a single polynomial, and you are saying the ideal generated by a single polynomial contains 1, so it will mean that that polynomial multiplied by some other polynomial is equal to 1, which will mean that that polynomial itself is a non-zero constant. But then of course I have assumed all the polynomials, the H's, so it will finally reduce to assuming that all the H's are constants, but then that will tell you that phi's are all polynomials, but I already assumed that phi does not come from a polynomial, so I again get a contradiction, okay. So so both these contradictions demonstrate that if you assume that this phi does not come from a polynomial, then you get a contradiction. So it means phi comes from a polynomial. Every regular function on the punctured plane is the restriction of a polynomial in two variables, therefore the map is surjective and we are done, okay. So that finishes the proof, and therefore the moral of the story is the punctured plane is an example of a quasi-affine variety which is not affine, okay. So we do have quasi-affine varieties which are not affine, alright. So I will stop here, and what I am going to do in the next lecture is I am going to tell about projective varieties and quasi-projective varieties, which are the more general varieties than affine and quasi-affine varieties, okay. So let me stop here.